Welcome back to the deep dive. If you're one of the millions of people who have spent hours, maybe even days, trying to perfect an instruction for an AI,
Oh, yeah.
just meticulously tweaking every little word, every comma,
Yeah.
that intense frustration, we're now calling it the manual iteration bottleneck.
It is such a bottleneck. I mean, that trial and error phase, it wasn't just frustrating, right?
Yeah.
It was computationally wasteful. It was completely unscalable.
And not repeatable at all.
Not at all. The early days of Gen AI were just people, trying to hack the model into doing what they wanted.
Exactly. But the whole industry is shifting, and it's shifting fast. We're moving away from that tedious work of the prompt engineer and more toward the elegant efficiency of being an AI agent designer.
Mm-hmm.
So our deep dive mission today is to really explore this concept of algorithmic optimization, the rise of the self-improving agent, and this huge paradigm shift called intent engineering.
That's the key term. We're moving from let's see what this prompt gives me to a much more scientific approach.
Yeah.
It's more like, okay, I have a defined measurable outcome. Mm-hmm. Now, how do I build and optimize a system that hits that target with, maximum efficiency? The focus just flips entirely.
It flips from the input to the output.
Exactly. From input structure to output performance.
And because we are diving into some pretty complex stuff today, genetic algorithms, hierarchical root cause analysis, we need a good metaphor to ground us.
Definitely.
So imagine we're in a high-stakes competitive kitchen. Our goal, to build the perfect bowl of Michelin-Star ramen.
I like it.
And we're going to talk about how we go from a really vague starting point, like make me some noodles, to this flawless optimized dish, all through algorithmic optimization.
So we'll unpack the core optimization cycle first, which is kind of the blueprint for this whole automated kitchen.
Okay.
And then we'll look at three fundamentally different chefs or algorithms.
Yeah.
There's the basic critic, which is the metaprompter, then the competitive kitchen.
The bake-up.
Yeah, the bake-off, using an evolutionary chef with genetic algorithms. And then finally, the real expert, the hierarchical chef, using HRPO, which is, just advanced root cause analysis to surgically fix failures.
Okay, let's unpack this. And I think we have to start with the foundational problem that anyone building an AI system faces. It's not a bug, it's just a reality. Our sources call it the impossible triangle.
Yes, the impossible triangle. It basically defines the constraints of any system, really, but especially AI agents. It's the relationship between speed, cost, and accuracy.
And the hard truth is, you can't have all three.
You can't. You can pick two, maybe.
Yeah.
If you try to maximize all three, you're pretty much guaranteeing failure, or at least, a very inefficient system.
It's like building a house, right?
Yeah,
you can have it fast and cheap, but the quality, the accuracy, the walls are going to be crooked.
Mm-hmm.
Or you can have it high quality and fast, but the cost is just going to go through the roof.
And that's our ramen analogy right there. The cheapest, fastest instant noodle packet. It tastes bland.
It's maximizing low cost and high speed, but it sacrifices the quality, the flavor, the texture. That's the accuracy of the dish.
So for an AI agent, if you want low latency, that's speed, and low token use, that's cost, you have to be ready for it to be, less accurate.
Especially on complex reasoning tasks. Precision just takes more steps. It takes more tokens.
And this tension, this is exactly why our methods for writing instructions had to evolve. We started out in what we'd call prompt engineering.
Right. That was, the early 2022 world, the manual iteration bottleneck. We were just hacking at the model's reasoning, just trial and error, changing words.
A verb here, an adjective there.
Exactly. And the whole process just failed from a scaling perspective. It was cumbersome. You couldn't repeat it. And this is the crucial part. It was unscalable. Every time a new model came out, a new version of GPT or Claude,
You had to start all over again.
you had to rinse and repeat the whole thing, even if the new model was way more capable. So we recognized that problem, and we moved into what you could call context engineering. This is where we got a bit smarter about giving the agent outside knowledge instead of cramming everything into the prompt.
This is where things like RAG, Retrieval Augmented Generation, came in. And advanced tool use, function calling, or MCP.
And that made a huge difference.
A massive difference. The agent could suddenly pull in external facts. It could perform actions.
But I want to pause here because even with our RAG and tools, there was still a fundamental philosophical error, wasn't there? The focus was still on the prompt first.
That's a great point. Yeah, you were still building this elaborate set of inputs and just hoping the model would get it right.
It was input-centric.
Totally. And it wasn't until we really pivoted to intent engineering that the philosophy actually flipped.
So intent engineering is the goal. It inverts the entire process.
Completely. You start with the outcome, the measurable evaluation. You work backward from there.
Like an architect.
Exactly like an architect. You define the building's requirements first, then you design the blueprint. You define what good looks like first. And the algorithm's only job is to build the system that achieves that outcome.
The intent-first approach feels like the real prerequisite for any of this automated optimization to even work.
It is. Without it, you're just optimizing for noise.
So to bring it back to the kitchen, Level 1 success means we have a formal quality check, we have an evaluation.
Correct. So the result is, okay, the noodles come out on time, the agent completes the task, it's functional. But it might be bland. It might use 3 times the tokens it needs to. The flavor might be a little off. It works, but it is not optimized.
It's not Michelin-Star.
Not even close. Level 1 is just proving you can make the dish. Now we have to automate the path to making it perfect.
Okay, so to get from functional to optimal, we need a system, a very formal system. Before we get to the different chefs, the algorithms, what are we actually tuning? What parts of an AI agent can an optimizer even manipulate?
That's a great question. For our purposes, you can think of an agent as having 3 main levers we can pull. The first, and the most obvious one, is the system prompt.
The instructions.
It's the core instructions, yeah. The persona, the rules, the constraints, basically the agent's identity.
And the second lever would be the tools it has access to.
Yes, the attached tools, the function calls, database queries, all the things that let the agent do more than just generate text. And optimizing that means, tweaking how the agent is told to use those tools.
And sometimes the tool definitions themselves, I imagine.
Sometimes, yeah. And then the third lever it's a bit more technical, is the language model component.
So the settings of the model call itself.
Exactly. The tunable parameters like temperature, top, frequency, penalty. You can totally change the output's creativity or its factualness without changing a single word of the prompt, just by adjusting those.
Okay, so those are the 3 levers. Now, what's the system that governs how they get improved? The optimization cycle. You said it's a 4-step blueprint that all the algorithms follow.
It's universally consistent, which is what makes it so powerful. Step 1 is input. You give it your starting point, your initial prompts, your data set of evaluation examples, and the most critical piece, the metric, the success criteria.
What does good mean?
We have to define good. Then step 2 is candidate generation. This is the creative part. This is where the specific algorithm, our chef, proposes new, varied prompts or recipes based on what it learned from the last round.
And this is where the different algorithms really diverge.
Completely. Their whole methodology for generation is different. Then step 3, and we have to stress this, is evaluation. This is the bottleneck for the whole thing.
The taste test.
The taste test. The system runs the new candidate against the data set, uses your metric, and logs the score objectively.
And finally, step 4 is result delivery.
Right. The optimizer gives you back the best prompt it found, a full history of what it tried, and all this standardized metadata. And that structured output is key, because it's what lets us chain these different methods together later on.
Okay, let's go back to that bottleneck, evaluation. You said the metric has to provide a really good signal.
An excellent signal. If your metric is vague or it's unreliable, the algorithm is just going to optimize for junk. You'll get better scores on a bad test, which is useless.
So how do we define good precisely? What kind of metrics are we talking about here?
You can group them into, let's say, simple heuristics and then the more complex LLM as a judge systems. On the simple side, if you're just measuring how similar 2 pieces of text are, you might use something like the Levenshtein ratio.
Okay, for listeners who aren't familiar, what is the Levenshtein ratio actually measuring?
It's basically the distance between 2 strings of text. It counts the minimum number of single-character edits, so insertions, deletions, or substitutions that you'd need to make to change one string into the other.
So it's good for checking format.
It's great for that.
Yeah.
If you need a specific JSON format, Levenshtein can tell you how close the output structure is to what you required, even if the content inside is a bit off. It's fast and reliable for structural stuff.
But that falls apart for things that have a definite right or wrong answer, like a math problem.
Exactly. For something like the GSM-8K dataset, which is grade school math, you use exact match. It's binary. It's either 100% right or 0% right. No in between.
No, the real world is messy. Most tasks are nuanced. They require judgment, summarizing a document, for example.
And that's where you had to shift to the LLM as a judge approach. You use another powerful, independent LLM, and you basically tell it, your job is to be the evaluator.
So you're using an AI to judge an AI.
Precisely. For metrics like checking for hallucination in the MedHalu dataset or checking for answer relevance in RagBench, you need that level of sophistication. A judge model can assess relevance, tone, coherence, things Levenstein just can't see.
And this detail seems really crucial. For the most advanced optimizers we're about to talk about, the judge can't just give a score. It needs to give a reason.
It absolutely has to. For an optimizer like HRPO, the metric must return a detailed reason for the score. It can't just be a number. That reason, that little piece of text, is the fuel for the whole optimization. Without that high-quality, actionable signal, the advanced algorithms just can't do their job.
Okay, so if we tie this back to the kitchen, achieving level 2 success means you've automated the recipe generation. You've replaced your own manual tweaking with a sort of brute force LLM iteration.
Yeah, you now have a shelf full of, say, 100 different ramen recipes that an AI critiqued and generated, and they're all better than your first bland attempt.
But still random.
It's still pretty random,
Yeah.
Or it's based on a very simple, single-objective critique. It's like having a shelf of high-quality ingredients but no system, no competitive refinement. We need level 3. We need algorithmic intelligence to guide the search.
Okay, so the simplest automated method we mentioned, the metaprompter, is basically just one chef critiquing his own notes over and over. It's better than us doing it, but to really go beyond that, we need competition. We need to explore.
And that brings us to the evolutionary optimizer. This is where we start using genetic algorithms. It's a huge shift in thinking. We stop treating prompts as these static individual things and start treating them as a biological population that evolves.
The competitive prompt bake-off.
That's a perfect way to put it, yeah. It incorporates real genetic concepts, selection, mutation, crossover, to search this massive, complex prompt space really efficiently.
So you start with a big population of prompts, a bunch of different recipes.
Right, maybe 50 or 100 to start. Each one gets scored against your metric, using that whole evaluation process we just laid out. And then the winners, the fittest prompts, they're selected to be the parents for the next generation.
So how do you breed a better instruction? How does that blending actually happen?
The main mechanism is called crossover or merge. So imagine one winning prompt has a great opening line, like, "You are a meticulous, non-judgmental summarizer." And another winner has a really effective formatting instruction at the end, like, "Always wrap your final output in XML tags." Crossover finds those effective components, those genes, and combines them. It creates a child prompt that hopefully inherits the best traits of both parents.
So you're taking the perfect broth from one recipe and the perfect noodles from another.
Exactly. But then you have to introduce a little bit of chaos. And that's the mutation phase.
Why is randomness so important here?
Mutation is absolutely critical to stop the population from getting stuck. You don't want it to get too uniform because then it gets trapped in what's called a local maximum.
It finds a good enough solution and just stops improving.
Right. So mutation injects randomness. It might randomly delete a constraint. It might swap the order of 2 sentences. It might replace a word with a synonym. And that unpredictability forces the algorithm to explore completely new parts of the prompt space where it might find a radically better solution.
And then there's this concept I find fascinating, elitism, or the Hall of Fame. It keeps track of the best ever prompt, but sometimes it gets rid of it. Why would you sacrifice your best one?
It's a deliberate strategy called forced exploration. So elitism makes sure you never lose your best performing prompt. If a new generation is worse, you can always fall back on the historical best.
That makes sense.
But if that elite winner is always winning, the population might stop evolving. So by occasionally, chopping it off, removing it from the breeding pool, you force the algorithm to find new ways to win. It's a risk, but it's a necessary risk to push for true innovation.
So evolutionary optimization is this powerful engine for exploration. But let's talk about a more sophisticated version that really tackles that impossible triangle we mentioned. That's GE.
GPA, yeah, the Genetic Evolutionary Pareto Search. It's a big step up because it understands complexity and it does multi-objective optimization.
What does that mean in practice?
So first, instead of treating the prompt as one giant block of text, GPA breaks it down into smaller pieces called prompt shards.
So like ingredients. The persona is one shard, the formatting rules are another.
Exactly. The spice blend, the plating instructions. And by treating these shards as the units of evolution, GGPA can be much more intentional about how it mutates and combines them.
But the real game changer is how it scores them, using the Pareto front.
That's the revolutionary part. Because in the real world, you don't just care about accuracy. You care about cost. You care about speed.
Okay, so explain the Pareto front and why it's so important for a production-ready agent.
A simple optimizer just tries to max out accuracy. It will chase that 100% score even if the prompt ends up costing $1 every time you run it.
Which is not sustainable.
Not at all. The Pareto front, on the other hand, it maps the trade-offs across all your objectives at the same time. So it might find a prompt that's 95% accurate but costs 50 cents. It might find another one that's 90% accurate but only costs 5 cents and is way faster.
And for a big company running millions of these a day, that 90% accurate prompt is the real winner. It's on the Pareto front.
Precisely. The Pareto front is this set of solutions where you can't improve one thing like accuracy without making something else like cost worse. GGPA specifically searches for that sweet spot. It finds the champion prompt based on the optimal balance for your business case, not just the raw score.
And GPA has this reflection mini-batch size requirement. What's that doing?
It means GPA isn't just mutating blindly. It needs to collect a certain amount of data, that's the mini-batch, before it reflects and decides what to try next. It's gathering enough success and failure data to intelligently guide which shards to combine or mutate. It's a little bit of that surgical approach we're about to see.
This gets us to our level 3 kitchen. We have a systematic, competitive way to improve our recipes, and we understand the trade-offs we need to make the dish commercially viable. But evolutionary methods are still, at their core, about exploration. They can be expensive. They can struggle with really, really big prompts, like the 20,000 token instruction sets you see in big companies.
They are fundamentally brute force, even if it's intelligent brute force. They try a lot of things until something works. And that's why HRPO, the Hierarchical Reflective Prompt Optimizer, was developed. It's the surgical chef.
It doesn't explore.
It doesn't explore. It diagnoses. And it fixes the root cause of why a prompt is failing.
So HRPO has to start with the evaluation. That's a complete reversal of the old way of doing things.
Yeah.
How does it begin that doctor's diagnosis?
It starts by looking at the evaluation results, specifically those detailed reasons for a failure from the LLM judge. It needs that rich diagnostic feedback. And then it systematically asks, why did this fail? Was the format wrong? Was the reasoning flawed? Did it hallucinate?
So it's not just seeing a low score, it's immediately categorizing the mistakes.
Yes, that's the hierarchical part. It groups failures into different failure modes. So if you run 50 tests and 15 fail because of bad formatting and 10 fail because the instructions were too vague, HRPO creates 2 buckets: format issues and vagueness issues.
Which keeps it from wasting time on the wrong problem.
Exactly. And once it has these buckets, it generates targeted fixes, or patches.
Yeah, patch.
Yeah, it reflects on each failure bucket and generates a corresponding strategy, or patch. So if the ramen diagnosis is too salty and the root cause is too much spice, the patch isn't try a whole new recipe.
Right.
The patch is a very specific instruction. Reduce the spice blend by 10% to prevent oversalting. These are small, targeted changes designed to fix one root cause without breaking everything else.
That sounds incredibly efficient. But also, how do you make sure all these different patches don't contradict each other when you put them all together?
That is the most complex part of HRPO. It's the synthesis step. The optimizer uses an LLM as a sort of meta-engineer to take all these generated strategies and merge them into one new cohesive system prompt.
So the LLM has to figure out how to integrate the reduce spice patch with the use XML tags patch without causing a new problem.
Exactly. It's essentially performing a focused, recursive refinement of its own operating system based on highly detailed diagnostics. The agent is literally rewriting its own foundational instructions.
It's a true self-improving agent.
And the performance numbers really back this up. The sources show that, using a decent model like GPT-4 Mini on standard datasets, the baseline score with no optimization was barely functional, but 11.85%.
And HRP.
HRPO jumped that average score to 67.83%. On some tasks, like complex question answering, it got over 92%. That leap from 11% to nearly 70%, that's the difference between a toy and a real production system.
So if the evolutionary optimizer is the competitive bake-off, HRPO is the dedicated Michelin-Star chef who tastes the dish, finds the exact flaw, too salty, identifies the root cause, too much spice, and prescribes the precise fix.
It is surgical, it's precise, and it's much more resource efficient than wide-scale genetic exploration. But, and this is the critical part, it is 100% dependent on the quality of that metric signal. Without a good reason for the failure, HRPO is completely blind.
We focused a lot on the system prompt, the main recipe, but we said there were other levers. So that brings us to the specialized optimizers that tune the other parts of the agent.
Right. This is where you get into the real precision engineering, tuning the specific ingredients around the main dish.
Let's start with the learning examples, the few-shot demonstrations. That's handled by the few-shot Bayesian optimizer.
Yeah, choosing few-shot examples manually it's really hard. The Bayesian optimizer tackles the problem of finding the optimal quantity, the optimal order, and the specific combination of examples to show the model. It uses Bayesian optimization to intelligently search for that perfect set.
And why Bayesian optimization for this problem?
Bayesian methods are just really efficient when you have a huge search space and every single evaluation is expensive, which is exactly the case here. Testing thousands of example combinations would take forever.
Yeah, right.
So instead of random testing, it built a probability model and intelligently suggests the next best combination to try, which gets you to the optimal set much faster.
So it's the ramen chef figuring out not just the best toppings, but the perfect order and placement of them in the bowl.
That's a great way to think about it. And then you have the parameter optimizer, which isn't touching the recipe or the ingredients at all. It's tuning the climate in the kitchen.
So temperature, top, frequency penalty, these abstract settings.
But they have a huge impact. Temperature controls randomness and creativity. Top controls token diversity. The parameter optimizer uses those same efficient Bayesian techniques to find the optimal settings for these, say, the perfect temperature between 0.3 and 0.5. It tunes the heat and the simmer time of the broth.
And this is where the whole systems architecture is just, it's brilliant. You don't have to use these tools by themselves. You can chain them together.
Yes.
How does that work, technically?
It works because of that standardization we talked about. Every GPA, HRPO, all of them returns a structured output, the optimization result object. It's a standard data schema.
Yeah.
There's the best prompt, the scores, the history, everything.
Which means the output from one optimizer can be the direct input for the next one.
Correct. You can design a flow. You can start with a broad exploratory search using GPA to get a good base structure and balance that accuracy-cost trade-off.
And then the prompt that GPA creates, which is pretty good but maybe still has some flaws, you would feed that directly into HRPO.
Exactly. HRPO then does its surgical, fine-grained failure fixing. And once HRPO has perfected the logic of the prompt, you take that prompt and feed it into the parameter optimizer.
For the final tune-in.
The final sampling configuration. It tunes the temperature and top for that specific perfected prompt to maximize speed in your production environment.
Yeah.
That sequential refinement. That's the pinnacle of the self-improving agent pipeline.
We should just touch on one last area, tool optimization. Optimizing an agent that uses function calling seems like a whole other layer of complexity.
It really is, because you're optimizing the interaction with an external system. And while GPA and HRPO can optimize the prompt that tells the agent when to use a tool, they generally don't optimize the technical definitions of the tools themselves.
And the sources mention a specific feature just for this.
Right. True tool optimization, so optimizing the schemas, the error handling, that low-level logic, is a specialized beta feature. And right now, it's only supported by the foundational Metaprompt Optimizer. It's a very specific, high-value problem that needs its own dedicated approach.
This has been a really, really deep dive. We've gone all the way from the frustration of just guessing with words to this incredibly sophisticated architecture of a self-improving agent.
I think the central takeaway for anyone building with AI is you have to embrace intent engineering. The quality of your final result is now directly tied to how clearly you can define your evaluation metric. You have to define success first.
And we've seen the three main ways to get there. First, the evolutionary approach, with things like GPA, which is fantastic for broad exploration, and for balancing those real-world business trade-offs of accuracy, speed, and cost.
Then the surgical approach, HRPO.
Yeah.
The diagnostic expert, it's efficient, it fixes complex problems, and we saw it achieved a massive, 56% improvement over the baseline.
Oh!
But it needs that high-fidelity metric. It needs the reason for the failure.
And finally, the precision tuners. The few-shot Bayesian optimizer for your examples and the parameter optimizer for your LMX call settings. And now we know you can Bayesian chain all of them together.
And the relevance for you, the person listening to this, is really simple but profound. This automation can cut down months of manual engineering time. It lets you move prompts between different models or just optimize your current system for huge cost savings, all by letting the AI critique its own recipe.
And here's where it gets really interesting, and this is our final thought for you to think about. These algorithms, especially the exploratory ones like GPA, they often find prompt structures and ways of phrasing things that a human would just never come up with.
We are essentially using algorithms to discover new optimal behaviors for agents that we didn't even know were possible. It's almost like a side effect in a drug trial that turns out to be more powerful than the original intended effect. We're finding these emergent optimal operating procedures through automated iteration.
So if the AI can handle the entire engineering and testing process, which these optimizers prove that it can, then the single biggest barrier left isn't the model's capability or even algorithm sophistication.
No.
It is purely our ability to perfectly and clearly define the success criteria. To provide that perfect high-signal metric that guides the whole process, we are now limited only by our capacity to define perfection.